OBS would ever load. Okay. Okay. Stream goals. I need to learn 2 years of advanced chemistry. So I have my exam in 22 days. I have 22 days until my exam. I haven't done anything for 2 years. Grade 11 and 12, I literally did absolutely no work, and my exam is now in person. Let's go! My exam is in person. I've never done a singular chemistry test, never done a single chemistry quiz, never done anything in chemistry in my life, and I have a grade 12 advanced chemistry exam. So I'm gonna have to do some of that. I also want to. Let me get Codex up here. I want to work on MEPUC CLI. So I have the CLI that I'm working on. It's for like long running agentic agents. Don't worry about it. But I need to work on it. I need to make physics presentation. I'm doing a physics presentation on, what am I doing it on again? This is still running. Oh yeah, I don't have Unit 5 yet, do I? Tough. I'm gonna be above the class if I just learn all of it, right? That's how that works, right? Money, all I got. Is this? Oh, this is actually hooked up, I think. Okay, so I also should probably study physics. Let me see. Conservation, momentum test, quantum presentation schedule. So I have a, oops, this guy dropped. Black body radiation and Planck's quantum hypothesis presentation that I haven't started. It's 30 minutes, a 5-mark multiple choice quiz, and this is on May 6th, so in 3 days. So Wednesday. Monday's a PA day, so I need to do that. I also need to finish my English assignment on dead internet theory. I have an English assignment on dead internet theory. I also need to catch up on quick writes in English. I should also probably study. Let's see what I'm doing in calculus. I already did my calculus test. Calculus is pretty light. It's May 3rd. May 1st is the test, PA day. Absolute Extrema. Optimization intro. Full disclosure date. So the next test is May 19th. The derivative of sine and cosine. Hold on. I tried to do this in class and I couldn't do it. Should I try to do it again? How would you even do that? You would need to use first principles. No, but you can. I tried to do it with French principles and it didn't work. So I don't know. Maybe I guess that's why we're learning it. How about yours today? Cause I'm gonna highlight it look like a bird. Real alaga. No. So let's see this. How this is going on. Computers. Okay. What? Why is there a blog about Greg, bro? what? What the hell is this? Oh. Oh, I see. She running that candy. This only works for 12 minutes? Sorry, Con, but I can't. So I just like go through this. What to know? That looks so fun. That's a lot. That's a lot of scrolling. Woo! Oh my god, I cannot wait. Okay, you know what? Well, I guess I have to started with it, right? About this unit, learn. Oh my god. You're joking. Chemical bonds. It wants me to do all of this? Sound God. What? This is one? You're joking. This is unit 1. Oh my god. These are all videos. How long are they? Oh.
This video we're going to...
My god, dude. Well, this is gonna be so fun. Okay, chemistry archive. Unit 1. Unit 3, Unit 4. Unit 4 looks small. Wait, what? Why is unit 1 so big? What is 1.1? Okay. This doesn't look that bad. Exam format MC. What does this mean? What is MC in SA? Make a 3-column flashcard table. Term, 7-word definition. One example. How you look like a bird. Money. All I got. Okay, well, let's go.
What I want to do in this video is discuss what it means to be a metal or metallic nature. So first, let's just think about the metals that we encounter in everyday life, or based on our experience, the things that we associate with being a metal. So the elements that really jump out at us as metals, we always refer to, hey, that's a metal, or that's metallic, are things like iron, or nickel, or copper, or silver, or gold, or aluminum. Or at least for me, these are the ones that immediately pop out. Hey, these are I've seen these things before, and they all feel like metals to me. But let's think about what's true about these things, and as we'll see many other elements on the periodic table that give them this metallic nature. What do we associate with having a metallic nature? Well, one is that these things can be shiny. These things tend to be shiny. There's kind of a gloss when light shines on it. They're not just kind of a matte color. They look metallic. Literally, that's sometimes the word that's used, where it has a metallic shininess to it. Another thing that we associate with is they tend to be fairly dense. If I take a block of a metal, and if I drop it into water, I imagine that's sinking, but not floating on top of the water. We also imagine them having a very high melting point. That they tend to be solid at room temperature. Solid at room temperature. And as we'll see, this is true of all metals except for one of them, which is mercury, which is shiny, but at room temperature, as
Hold
is
on.
in its liquid form. Now, the other things that I associate with a metal is that I can make things out of them I can bend them and shape them in different ways. If I think of aluminum foil, I can bend it. It's not just going to crack. I can bend it and put it into different shapes. Even things like iron, it might take a lot of pressure to do it, but they're bendable, they're malleable, and definitely things like gold and silver and copper, you can actually mold into different types of jewelry. If you put pressure on it, it's more likely to bend than crack and just kind of shear off. So let's put malleability. They're malleable. And the other thing that I associate with metals is that they conduct electricity well. Conduct electricity. A place that you'll see metal in your life is if you open up your electronics, you'll see wires that might be made out of copper, or you might have components that are made out of other metals like gold or silver or whatever else. So given that these are some of the properties that we associate with metals, let's think about what's happening at the atomic level to give these elements these properties. The way I think about it, let's just go with copper for a second. Let's just imagine a block of copper at the atomic level. So let's say this is one copper nucleus right over there, and it has its sea of electrons. Just like, or not sea of electrons, it has all of its electrons in the various orbitals. We'll talk about sea of electrons in a second. But this is kind of a cloud of electrons, I should say. So this is electron cloud. So the electrons are just jumping around in this cloud. It's really a probability density. There's kind of a certain probability that could be at any point in that cloud. And so let's imagine a big solid piece of copper. So you would have a bunch of these. All together, all forming the solid. And what allows metals to be malleable, to do things like conduct electricity, which is the movement of electrons, is essentially for that they're very willing to share electrons with each other. By sharing electrons, so you can imagine this is one copper atom, that's another, let's say they're sharing some electrons. That's what allows the electricity, or this flow of electrons, to happen. If these electrons are loosely bound, then if you put a potential difference, a voltage, let's say that you put a potential difference so that this side is more negative and then this side is more positive, then the electrons are going to want to get away from the negative charge, move towards the positive charge. And if they're relatively freely bound, they can kind of move from one cloud to the next, and you kind of end up having what's often called a sea of electrons. Let me write that down. You have a sea of electrons, which would make this conductive. That's why you see so much wire made out of copper. And the sea of electrons is also what makes it malleable. If someone on this side would put a lot of pressure this way, and on that side put a lot of pressure that way, things that are rigid would just kind of crack and break, right? Would just break right over there. But because you have the sea of electrons, it allows it to be malleable. This part might just bend down a little bit, that part might bend up, but the metallic bond is not going to break. And so given that this metallic nature really comes from the willingness of these atoms to share electrons with each other, to create the sea of electrons, I encourage you to pause this video and think about which atoms on the periodic table, which elements are more likely to do that, to share electrons with others and with each other. And really this is the same principle that we thought about ionization energy and electronegativity. So pause the video. So I'm assuming you've had a go at it. So which elements are most likely to share electrons? Well, we've already seen that
the things that are
from the left side of the periodic table of elements, group 1, for example, they only have one valence electron. It would be very hard for them to get enough electrons to complete that.
So the more of what valence, this is one valence electron, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8.
Outer shell.
And then these are
they get rid of that one valence electron. They can go to a more stable state. So they really want to give away electrons. And the ones over here, they're so close. If we talk about the halogens, they're one electron away from completing their outer shell. They're greedy. They want to hog these electrons. They tend to be electronegative. The noble gases, they're done. They definitely don't want to share electrons with anyone. They're kind of in a very stable state. Now, the other thing that we've talked about is as we go down a group, our atoms are getting larger and larger and larger. So the outermost, that 55th electron in cesium, is much more loosely bound because it's further away than the, say, the third electron in lithium. So just as we saw as the elements in this bottom left have very low ionization energy, it doesn't take much energy to remove an electron from them. These are the ones that are most likely to share electrons. And these actually have the highest metallic nature. So high metallic nature. And the ones on the top right, these are going to be the opposite. They're very unlikely to share electrons. These are very electronegative. They have a very high ionization energy. They have a low metallic nature.
The minimum energy required to move the most loosely bound electron. Okay. That makes sense. So these are low ionization energy, these are high ionization energy. It increases to the top right. That makes sense. So ionization energy is like how much energy it takes to move the least.
So I can imagine some things are popping into your brain at this point. We started thinking of the elements that in our everyday life we associate with metals. But what I'm saying is that these things over here have an even higher metallic nature. But what about something like calcium? Every day when I typically, or when a lot of people imagine calcium, they think of kind of a white, chalky substance, very rigid, not very malleable, not very good, not very shiny, not very good at conducting electricity. Based on what I just told you, this would have a higher metallic nature than something like aluminum. What you have to remind yourself is that what you see is not actually pure calcium. That kind of chalky thing, that's calcium carbonate. Pure calcium, actually, this is actually a picture of pure calcium.
Okay, this just kind of looks bad, just like in general. Why am I using the CLI for this? Multitasking at its finest. I need to run You're gonna make me angry, bro. Oh my god, Amethyst is the worst goddamn software I've ever seen in my entire life. Okay, this kind of looks terrible. The UI looks terrible. The NEPUC CLI in the top left has like the red, yellow, and green. Why do you have that? Just like completely remove that. The daemon should just like, why would it show me that it stopped? Remove that, because it should be running whenever I run UV run NEPUCs. It should be running when I'm actually using it. When I send messages into the left, I need to be actually talking to the model. Also, during the setup, I don't just want to see like random stuff. Like I want to make it so when I run the first command, I run the setup, and then it asks me which model I want, and this all happens in the UI. It asks me which connector I want to connect to, but it suggests a local model, and then asks for your endpoint. We'll focus on that later. On the right side of the screen, like so when you run the slash command, the up and down arrows just like don't work at all for going up and down. It also looks really bad. I need you to take inspiration from other places, like OpenCode and how their slash works. You need to literally I'll copy an image right now. You need to take inspiration from other places, because this entire thing just looks really bad, and it can be much more simplistic and look a lot better. The ASCII art can be better, the fonts can be better, the sizing is really bad. It's all like improperly sized. You need to think about this extremely long and try to make all of this work. Like why can I not run goals in this? Oh my god, did I just cook myself? Okay, thank God. Computer use, browser use. No. What is this? Developers not. What is this? It doesn't even. Okay, well. Kill me now. slash goal. I don't know if it works, but
and it is shiny. It does have these metallic properties. So the general trend here is that all of these, this is very high metallic nature, and these are very low metallic nature, which also makes you probably realize, wow, most of the periodic table is a metal of some form. If aluminum is a metal and all of these things have a higher metallic nature, then all of this stuff are metals, and that is the case. The S block, the D block, the F block, these are all metals, and then a good chunk of the P block, are considered metals, and these are kind of sometimes referred to as metalloids. And this section of the periodic table is not considered a metal. That makes sense. Noble gases, they are gases. They're not very reactive. They don't bond, so they don't form kind of a structure that can even do this type of thing. And these other ones over here, even carbon, when it formed a lattice, it does not conduct electricity well. It tends to not be so malleable. If you think about something like a diamond, or if you think about, well, a diamond might be the best example of that. So anyway, hopefully this gives you a sense of metallic nature and the trends in the periodic table. High metallic nature, and as you go to the top right, lower and lower metallic nature.
because their ionization energy decreases.
Electronegativity is probably the most important concept to understand in organic chemistry. We're going to use the definition that Linus Pauling gives in his book, The Nature of the Chemical Bond. So Linus Pauling says that electronegativity refers to the power of an atom in a molecule to attract electrons to itself. So if I look at a molecule, I'm going to compare two atoms in that molecule. I'm going to compare carbon to oxygen in terms of the electronegativity. And to do that, I need to look over here on the right at the organic periodic table, which shows the elements most commonly used in organic chemistry. And then in blue, it gives us the Pauling scale for electronegativity. So Linus Pauling actually calculated electronegativity values for the elements and put them into the table, and that allows us to compare different elements in terms of their electronegativities. For example, we are concerned with carbon, which has an electronegativity value of 2.5, and we're going to compare that to oxygen, which has an electronegativity value of 3.5. So oxygen is more electronegative than carbon. And the definition tells us that if oxygen is more electronegative, oxygen has a greater power to attract electrons to itself than carbon does. And so if you think about the electrons of the covalent bonds between carbon and oxygen that are shared, they're shared unequally because oxygen is more electronegative. Oxygen is going to pull those electrons in red closer to itself. And since electrons are negatively charged, the oxygen is going to get a little bit more negative charge. And so it's going to have what we call a partial negative charge on it. So partial negative. Its partial sign is a lowercase Greek letter delta. And so the oxygen is partially negative. It's pulling the electrons in red closer to itself. Another way to show the movement of those electrons in red closer to the oxygen would be this funny arrow here. So the arrow points in the direction of the movement of the electrons in red. So carbon is losing some of those electrons in red. Carbon is losing a little bit of electron density. Carbon is losing a little bit of negative charge. So carbon used to be neutral, but since it's losing a little bit of negative charge.
Okay, well, this isn't going well. I don't understand this.
This carbon will end up being partially positive like that. So the carbon is partially positive and the oxygen is partially negative. That's a polarized situation, right? You have a little bit of negative charge on one side, a little bit of positive charge on the other side. So it's still a covalent bond, but it's a polarized covalent bond due to the differences in electronegativities between those two atoms. Let's do a few more examples here where we show the differences in electronegativity. So if we're thinking about a molecule that has two carbons in it, and I'm thinking about what happens to the electrons in red. Well, for this example, each carbon has the same value for electronegativity, right? So the carbon on the left has a value of 2.5, the carbon on the right has a
What is this? The Pauling scale for electronegativity. So these are the values of it.
value of 2.5. That's a difference in electronegativity of 0, which means that the electrons in red aren't going to move towards one carbon or towards the other carbon. They're going to stay in the middle.
But if it's positive, it's going to go this way, and if it's negative, it's going to
They're going to be shared between those two atoms. So this is a covalent bond, and there's no polarity situation created here.
There's no polarity situation created.
Since there's no difference in electronegativity. So we call this a nonpolar covalent bond. Right, so this is a nonpolar
Polar bonds mean type of what's covalent bond mean? A type of chemical link formed between atoms, typically non-metal, shared pairs of valence electrons to achieve stability to fill. Share pairs of valence electrons to achieve so that's a covalent bond. A polar bond is a type of covalent bond where the electrons are shared unequally between two atoms. How does that even make sense? How is that possible?
polar covalent bond like that. Let's do another example. Let's compare carbon to hydrogen. So if I had a molecule and I have a bond between carbon and hydrogen, and I want to know what happens to the electrons in red between the carbon and hydrogen, we've seen that carbon has an electronegativity value of 2.5, and we go up here to hydrogen, which has a value of 2.1, and so that's a difference of 0.4. So there is a difference in electronegativity between those two atoms, but it's a very small difference. And so most textbooks would consider the bond between carbon and hydrogen to still be a non-polar covalent bond. All right, let's go ahead and put an example we did above, right, where we compared the electronegativities of carbon and oxygen.
So
that when we looked at the values, we saw that carbon had an
lot?
electronegativity value of 2.5, and oxygen had a value of 3.5 for a difference of 1. And that's enough to have a polar covalent bond, right? This is a polar covalent bond between the carbon and the oxygen. So when we think about the electrons in red are pulled closer to the oxygen, giving the oxygen a partial negative charge. And since electron density is moving away from the carbon gets a partial positive charge. And so we can see that if your difference in electronegativity...
What is polar covalent bond? Important question. A covalent bond is where electrons are shared unevenly between two atoms, causing therefore a slight polar charges on each atom because each has a higher electron than the other. Is the difference in electrons less than 0.5? Depends on the source.
is 1, it's considered to be a polar covalent bond, and if your difference in electronegativity is 0.4, that's considered to be a non-polar covalent bond. So somewhere in between there must be the difference between non-polar covalent bond and a polar covalent bond. And those textbooks will tell you approximately somewhere in the 0.5 range. So if the difference in electronegativity is greater than 0.5, you can go ahead and consider it to be mostly a polar covalent bond. If the difference in electronegativity is less than 0.5, we consider that to be a non-polar covalent bond. Now I should point out that we're using the Pauling scale for electronegativity here, and there are several different scales for electronegativity. So these numbers are not absolute, these are more relative differences, and it's the relative difference in electronegativity that we care the most about. Let's do another example. Let's compare oxygen to hydrogen. So let's think about what happens to the electrons between oxygen and hydrogen. So the electrons in red here. All right, so we've already seen the electronegativity values for both of these atoms. Oxygen had a value of 3.5, and hydrogen had a value of 2.1. So that's an electronegativity difference of 1.4. So this is a polar covalent bond. Since oxygen is more electronegative than hydrogen, the electrons in red are going to move closer to the oxygen, so the oxygen is going to get a partial negative charge, and the hydrogen is going to get a partial positive charge like that. All right, let's do carbon and lithium now. So if I go ahead and draw a bond between carbon and lithium, and once again, we're concerned with the 2 electrons between carbon and lithium. The electronegativity value for carbon, we've seen, is 2.5. We need to go back up to our periodic table to find the electronegativity value for lithium. So I go up here and I find lithium in group 1 of my periodic table has an electronegativity value of 1. So I go
1 lithium. So do like normal periodic tables have that? No. So what the hell is this periodic table? It's
go back down here, and I go ahead and put in a 1. And so that's a difference in electronegativity of 1.5. So we could consider this to be a polar covalent
so you're saying a polar covalent bond in the term of
bond. This time carbon is more electronegative than lithium. So the electrons in red are going to move closer to the carbon atom. And so the carbon is going to have a little bit more electron density than usual, so it's going to be partially negative. And the lithium is losing electron density, so we're going to say that lithium is partially positive. Now here I'm treating this bond as a polar covalent bond, but you'll see in a few minutes that we could also consider this to be an ionic bond, and it just depends on what electronegativity values you're dealing with, what type of chemical reaction that you're working with. So we could consider this to be an ionic bond. Let's go ahead and do an example of a compound that we know for sure is ionic. Sodium chloride, of course, would be the famous example. So to start with, I'm going to pretend like there's a covalent.
So I'm looking at the first couple of videos of the first lesson right now on Khan Academy, and I'm like not understanding like at all. Like they're talking about, so I'm watching the electronegativity and bonding. You need to go through like pretty much every single one of these videos that you're looking at and fully understand what I'm being taught, because I don't understand a lot of the stuff that he's saying. He's talking about different types of bonds and covalent bonds and covalent bonds and ionic bonds. I don't know like any of this. Again, I didn't learn any of grade 11 chemistry. You need to teach me a lot of the grade 11 chemistry too, just like stuff. So I know just general terminology. I did do grade 10, so I know like a couple like things on the periodic table and stuff, but that was very, 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 very basic. I still don't know a lot of this stuff. It needs to be like pretty much from scratch. I need to know like all of this stuff. Like I'm going to paste in the success criteria, and you need to make me an entire study guide with everything, all YouTube videos. It doesn't have to be from Khan Academy. YouTube videos of every single thing. And they need to actually include things that someone who doesn't really understand it. If there's something that is in the video that I wouldn't understand, you need to add another video of something that I would understand, or teaching me that thing that I didn't understand. Think hard on this. Bro, what? Bro, what the hell is this? What do you mean you recognize this guy, bro? What do you mean website preview, bro? There's literally again, I just opened it and I don't see anything. I open the CLI and there's no thing to go through. Like there needs to be an install process. There needs to be an install process on the right. There's like you can't just add things to the right and say setup. These are the things. Like there needs to be a full actual install process. Remove this entire goddamn UI. I want you to start from scratch. This UI looks horrendous. Remove the entire thing. Just throw the entire UI out the window. I only want to keep the back end. This UI looks horrible. It's a horrible start. It was a horrible way to go through it. You just need to remove this entire UI and start from scratch. This is horrible. You need to actually use your coding skills and your coding ability to make a good looking UI. It needs to actually look usable. This is literally fully unusable right now. There needs to be an install process. When I install the thing, there needs to be a full process to install and ask which models you want. Like ask API key, like if you want to start a job, like running through the doctor, like the arrow keys just don't work. It's just a complete mess. It's horrible. I'm actually gonna take this and I'm gonna go to Codex /resume. I'm doing a /goal, I don't care. What do you mean, bro? I'm setting a goal for this. What? Claude Max in 2010. 100. Well, I would be 2 years old. But if I wasn't 2 years old, Claude Max in 2010. What am I doing, bro? Lock in. There's no way. Andrew Huberman. Bruh. X is so cooked, bro. I got a son, what you find? You're just a little bit late. I guess you're already died. Watching patterns unfold into AGI. Hold on. I need to do that. I got a son, what you find? You're just a little bit late. Whoa. What photos did I just leak to the entire world? Do I need to delete the stream? Bruh. I think we're good. I think we're good. I think we're good. Let me try one more time. That's the wrong one. Yeah, we're good. It's just me. It's just pizza. Pictures of food. I hate you. But like, why? Can someone explain to me how this is somehow a smart move by Buffett? Because frankly, it seems like it's a pretty big failure on the part of Picture. The more the better, what?
Let's take a closer look at atoms. Atoms are the building blocks that make up everything, all stuff, everywhere. Here I've got some drawings. This is table salt, a solid. Here's water, a liquid. And finally, oxygen gas. And what we're looking at here is what we'd see if we could take these three things and zoom in zillions and zillions and zillions of times. And if we could look at these closely enough, we'd be able to see that atoms, these little building blocks that make everything up. Now, atoms aren't really little colored circles, but it's a good way to think about them. It's the way we usually draw them when we're learning about this stuff. Atoms are super tiny. They're so tiny, it can be really hard to wrap your head around how tiny they are. Here's something that might help you think about this. Take a piece of paper. Look at how wide it is here. All right, this is so incredibly thin. Now, atoms are so small that it would take 1 million atoms lined up next to each other in a row to be as thick as this tiny width of paper. That's how small atoms are. Now, what I want to do now is look even closer at an atom. Let's take one of these atoms here and zoom in even more so we can see what's inside it. Here's a magnified view of one atom. It's not a perfect representation of exactly what an atom looks like, but it's close enough for right now. And check this out. The atom itself is made up of even smaller things. Right, so we said atoms are like a building block for all stuff, but then if you look at an atom, it has even smaller building blocks that make it up. So in the center of the atom is something called nucleus. And the nucleus is made up of two tiny particles. There are protons, which are drawn as red circles here, and there are neutrons, which are drawn as blue circles. Nucleus here in the middle of the atom. And then on the outside of the atom, there are the moving. They're for a number of reasons. Charge. And that has important consequences for how this atom works. We said these electrons are flying around the outside of the atom. They're moving, just flying away. But the electrons are moving around so fast that they're not able to actually pull in here and actually touch the protons. So that's why they keep staying on the outside and don't just crash in here and all touch the protons. Now sometimes people ask neutrons. Neutrons don't have charge. Why are they important at all? Well, it seems that neutrons help keep all the particles in the nucleus strongly connected to each other. Now electron charge is important. Something else that's important with atoms is what their mass is, how much they weigh. So in order to figure that out, we have to look at the mass of the various things that make up the atom. Now a proton and a neutron are very, very similar in size and mass, and they both weigh about this many grams. Look at what a tiny number this is. Right? There's a decimal place all the way over here. This is a number that is best to represent in scientific notation instead. But however you write this, it's a really tiny, unwieldy number. So scientists came up with another way to measure the mass of a proton or neutron, and that's using a unit called the AMU, the atomic mass unit. And they said, okay, one proton or one neutron weighs about 1 AMU. That's a lot easier to use than this measurement here. So a proton or neutron weighs about 1 AMU. An electron, on the other hand, is much, much, much smaller than a proton or neutron. It weighs only 0.000549 AMU. So a tiny fraction of how much a proton or neutron weighs. For this reason, when we're talking about the mass of atoms, which we'll talk about later on, we usually add up the protons and neutrons to find out how many AMUs the atom weighs. And then we usually don't even worry about the electrons at all because they're so tiny. They don't really have much of an influence on how much an atom weighs. It's like when you get on a scale to weigh yourself, you don't worry about the ring you're wearing or whether you're wearing a necklace or something because those things are so tiny, they weigh so little compared to how much you weigh that it doesn't really influence your weight. So protons, neutrons, 1 AMU, and electrons, a tiny fraction of that. Now, since the atom weighs drawn here isn't a perfect representation of what atoms would actually look like. We'll talk more.
Goal achieved in 11 minutes. Like, bro, what the?
More about that later. There are two things I want to wrap right now. The first is the electrons and how they move. This drawing might make you think that the electrons are spinning around in nice circles on the outside of the atom. That's actually not what happens. They're buzzing around much more randomly, kind of like hyperactive flies all over the place. We'll talk more about that later. The second thing has to do with the size of the nucleus and how far the electrons are from it. If this were a real atom blown up many, many times, and the nucleus were the size of a grape, the electrons out here would be almost a mile away. So this grape-sized nucleus, and a mile away would be the electrons spinning on the outside. So that means that most of an atom is actually empty space. Anyway, now we've talked about what an atom looks like, the particles make it up. We can go discuss some of the characteristics that we can use to describe atoms. These are things like
periodic table and valence electrons.
In the next couple minutes, we're going to talk a lot about electrons. First, we're going to start out looking at an atom and looking at the spaces in an atom where electrons can live. Then we'll learn about the most important type of electrons in an atom. These are called the valence electrons. We'll learn how you can figure out how many valence electrons an atom has by looking at where that atom is on the periodic table. And finally, we'll look at how you can take an atom and draw one of these electron dot diagrams for it that shows how many electrons it has. So let's get started. Okay, so check out this diagram of an atom I have here. In the middle is the nucleus with protons and neutrons. And now look at all of these little circles. Each one of these circles represents a spot that could hold one electron. You can think of these as like parking spots for electrons, or like theory seats for electrons. And these spots for electrons are organized into these circles. These circles are called energy levels, or shells. You can think of these energy levels or shells sort of like they show the path that the electrons would take as they're spinning around the nucleus here. But also, energy levels or shells arrange electrons into different groups that are varying distances from the center of the atom. Okay, like so for this first group, this first energy level or shell can hold 2 electrons, really close to the nucleus. Moving out a little bit, we get to another shell that can hold 8 electrons, and they're spinning out here. And then even further out, we have another group that can hold 8 electrons. Now, it keeps going from here, and there are more and more energy levels or shells. But it gets a little bit tricky, so I just want to focus on these first 3 to give you an idea of how they work. Now, if you learned a little bit about atoms already, you might know that the way I've drawn this here, this is the most perfectly accurate way to represent electrons and atoms. But you know what? It doesn't matter. For our purposes right now, we just want to learn the basics. Drawing and thinking about atoms like this is totally fine, so don't worry that it's not super accurate. Okay, so let's look at what happens when we start filling these electron parking spaces, when we start filling them with actual electrons. So we're going to use a periodic table for this. We'll go column by column. And here's what I'm doing. I've made this big version of a periodic table. You can see it looks a little bit different than the real version of a periodic table. Okay, look at this whole thing in the middle. This is sort of a big real periodic table. We're not going to worry about any of these elements in here in the middle. So this whole section, I put it here. Just got rid of it. We're not going to worry about it. We're only going to focus on 8 columns. We're going to focus on these 2 right here, which I've drawn there, skipping everything in the middle, and then we're going to focus on these 6 over here. So don't get confused by the way I've drawn this. We're just leaving out some of the elements that we don't want to get to right now. Okay, so let's take the first element right here, hydrogen. Now, how many electrons are there in hydrogen? Okay, well, we're going to look up on the periodic table, and we're going to find something like this. Now, the periodic table, it doesn't actually tell us how many electrons are in hydrogen. It's got this 1 here, but that refers to the number of protons. There's 1 proton in hydrogen. That's what its atomic number is. Now, if we assume, though, that this hydrogen atom, if we assume it doesn't have a charge, then the number of electrons is going to equal the number of protons. So hydrogen always has 1 proton, but if the atom is neutral, it doesn't have a charge, it will also have 1 electron. So let's go back to this diagram here. Let's just start with this first energy level. Okay, here's the first energy level. Let's put a nucleus in here. I'm not actually going to draw the protons and neutrons. Instead, I'm just going to write the number of protons. Okay, so this has 1 proton, and P plus is the abbreviation for proton. So 1 P plus in the nucleus. Now here are the 2 spots in this first energy level where electrons can live. There is 1 electron in hydrogen, so we're going to fill that in. That was really easy, right? So we got this first energy level in hydrogen. 1 of the spots is still empty, and 1 of the spots is full. Okay, let's move down here to lithium. Now if we look up lithium on the periodic table, we're going to see this 3, which means that every lithium atom has 3 protons in it. If that lithium atom is neutral, which we always assume it is when we're doing this sort of thing, this lithium atom also has 3 electrons. So we'll start here. We'll be first concerned with this this energy level that's right here, the first one here. I'm going to put a nucleus in here, 3 P plus because there's 3 protons in here. Okay, so there's 3 electrons. So this one's going to get filled, and this one's going to get filled. And now we're going to want to go to the next energy level. Okay, now that starts to get filled. So now it's going to look like this. Now we're going to start thinking about the second energy level. The first one's filled, and now 1 electron is going to go here in the second energy level. Okay, so these energy levels, they're really like parking spaces. Imagine the nucleus is a mall, right? It's like the parking spaces closest to the entrance of the mall. Those are the ones that fill up first, and as more and more people park, the empty parking spaces move further and further and further away from the center of the mall. It's exactly the same way with atoms. Okay, the first energy levels close to the nucleus, those are the ones that are going to fill up, and then after they're full, the other energy levels further out, they're going to be filled too. Okay, now let's look at sodium. Sodium has 11 protons in its nucleus, 11 P plus, and we're going to assume that since it's neutral, we're assuming that it's neutral has the same number of electrons as protons. So let's start filling it. 1, 2 in the first energy level. Now that's full, so we're going to start filling the second energy level. 3, 4, 5, 6, 7, 8, 9, 10, and finally these are all full. We still have more electrons. Now we're going to have to bump it to the third energy level. Here's the third energy level we can start filling in. 10 of these are already living out, so we're going to add 1 more, and now there's 1 in this third energy level. Okay, now check this out because this is important. Hydrogen, lithium, and sodium, they all have different numbers of electrons. But there's a pattern here. Check this out. Each one of these atoms has 1 electron in the outermost shell. Okay, this one's full, then there's just 1 here. This one's full, and then there's just 1 here. And then hydrogen only has 1 energy level, and it just has 1 electron. These electrons, 1, 1, and 1, these are the valence electrons, the most important electrons in an atom. We'll talk more about that later why they're so important. But all you have to know for right now is that the valence electrons are the electrons in the energy level that is the furthest out from the nucleus. So in this atom, the valence energy level is the third, and it has 1 electron. And here, the valence energy level is the furthest out is the second, and here, the furthest out the valence energy level is the first. So there's a pattern. Each one of these atoms has 1 valence electron. That's true, not just for these first 3 atoms, but for every one of the atoms that's in this first column in the periodic table. I didn't want to do the electron structures for all of these others, but just trust me that they all have 1 electron. Okay. So now there's a way that we want to be able to write that to show that these elements have 1 valence electron. And what we can do is draw what we call these electron dot diagrams. They're sometimes known as Lewis diagrams, where we take the element and then put 1 dot over it to show that it has 1 valence electron. Here's how we write the electron dot diagrams for all the elements that are in this column. As an example, I'll just take lithium and write it here. So every single atom in this column has 1 valence electron. Okay, let's move on and take a look at some of the other columns on the periodic table. Okay, so everything here has 1 valence electron. Let's take a look at this column. Starting with beryllium. Beryllium has 4 protons. If it's electrically neutral, it's going to have 4 electrons as well. So let's look at how this fills in. We've got 4 protons here in the nucleus, and now we're going to go 1, 2 in the first energy level, and in the second energy level, 3, 4. Okay, so we've got 2 electrons in the outer energy level. Look at my filling in. I just filled them in clockwise here, but 1 electron and then 1 went on the bottom. Okay, now magnesium. Magnesium here has atomic number 12, so 12 protons and 12 electrons. We assume that it is electrically neutral. 12 P plus here. So 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what's the pattern here? For this second column in the periodic table, we've got 2 valence electrons for magnesium in the third energy level, and we have 2 valence electrons for beryllium in the second energy level. So everything in this column has 2 valence electrons in this outermost shell. So what we can do is we can draw electron diagrams for everything in the second shell here. I'm sorry, for everything in the second column here. And it looks like this. We take the element symbol, and then we put a dot at the top and a dot at the bottom. And that's how we represent the electrons for here. So I'll just do like Be beryllium, for example, Be dot at the top, dot on the bottom. What's going on? Okay, you're probably getting the hang of this, so we're going to start moving a little bit faster. So we've got a boron here. Here's boron. This is the structure of boron. And then here is aluminum down here. 5 protons, 13 protons. And look at what the structure of the valence electrons is here. We've got 1, 2, 3 in the valence shell of boron. And for aluminum, we've got 1, 2, 3 in the valence shell. The same is true for these guys here, even though I haven't drawn out. So if you're in this column, you have 3 valence electrons. An example of this would be boron. And look at how I do the dots for boron. Okay, I do a dot on the top, just like lithium. I do a dot on the bottom, just like beryllium. And then I do a dot here to the left to show that these all have 3 valence electrons. It would be the same way for any of the elements in this column here. Okay, let's do all of these as a group. Okay, this column first has carbon and silicon. And each of these have 1, 2, 3, 4, 1, 2, 3, 4 valence electrons in their outer shell. Okay, so I can take this and do a dot here, a dot down here, a dot to the left, and then a dot to the right to show that everything in this column has 4 valence electrons. Now moving on to the right, we've got this column with nitrogen and phosphorus and all these others. And everything here has 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 valence electrons. So if nitrogen is my example, I'm going to do N, down the top, down the bottom, left, right, and now I start doubling up. So now there are going to be 2 dots on the top of nitrogen to show that there are these 5 valence electrons for everything that's in this column. You can probably see that there's a pattern that's developing here. Oxygen and sulfur each have, you can count them 6 valence electrons. I'll take oxygen as an example. Now look what I do here for drawing the valence electrons because it gets a little bit tricky. You'll figure out. It's a little bit tricky. Okay, down the top. So 6 valence electrons for everything in this column. Oxygen is the example. Down the top, down the bottom, down the left, down the right. Now we double up the one on the top and then we double up the one on the right. Okay, so we double up on the bottom, we put it on the right. So up, down, left, right, and then around clockwise. Finally for this column, which has at the top of it fluorine and chlorine, both of these have 7 valence electrons, which means that the valence shell is almost full except for one hole in it. So I'll take fluorine as my example here. Down on the top, down on the bottom, down on the left, down on the right. Now we double up on the top, 2 up here, double up on the right, 2 there, and then double up on the bottom. So I've only got one guy here on the left that doesn't have a pair. Now here's the last column we're going to talk about. Okay, look what happens here. We'll look at helium, neon, and argon. Okay, here's helium, here's neon, and here is argon. Notice that argon has 8 valence electrons, doesn't have any empty holes in its valence shell. Neon also has 8 valence electrons, but helium only has 2 valence electrons. Okay, so what's going on in this column is that most of these have 8. Neon has 8, argon has 8, as do krypton, xenon, and radon. But then there's helium that only has 2. But regardless of whether you have 2, or whether you have 8, or whether you have 2, if you're in this column, your valence shell is totally full. Okay, so here's full of 8, here's full of 8, and here's full of 2. But they're all full, and there aren't any empty holes in the shells. So as an example, I'm going to use neon, which has 8. So 1, 2, 3, 4. Now we go clockwise. 5, 6, 7, 8. 8 valence electrons for most of these guys. Remember that helium only has 2 valence electrons, but all of them have valence shells that are totally full with no empty spots. So this kind of sums up everything we talked about. Every atom in this column has 1 valence electron. Every atom in this column has 2 valence electrons. And then we skip over this middle section, and we get 3, 4, 5, 6, 7, and 8. So if you know which of these columns a particular atom is in, you can figure out how many valence electrons it has.
I got us electrify. You're just a little bit late. I guess you're already died. No, main group of metals tend to lose electrons.
Okay, what's an ion? People talk about ions all the time in chemistry. So what are they? Well, an ion is an atom or a group of atoms that have an electrical charge. Okay, that's all it is. Now, how does this happen? Well, inside atoms, there are 2 things that have an electrical charge. There are protons that have a positive charge and electrons that have a negative charge. A lot of times in atoms, the number of protons is equal to the number of electrons. So the charges balance out and you don't have any total charge. But sometimes an atom can gain or lose electrons, so it gets more or fewer electrons and protons, and then the numbers don't balance out anymore, and it's left with more negative charge because it has more electrons, or it's left with more positive charge because it has more protons. Let me give you a couple examples of how this happens. Let's look at the atom sodium. Sometimes when I'm talking about atoms, I'll just draw them as the element name inside a circle to indicate that that's the atom I'm talking about. But for our purposes, we're going to want to zoom in a little bit more. Here I've drawn 2 things in the zoomed in version of the atom. I got protons here in the nucleus in red, and then flying around on the outside, I have these electrons, which I've drawn as black dots. If you know a lot about atoms, you might know that I've left out the neutrons, which also live in the nucleus. But it's no big deal because neutrons don't have a charge at all. They're neutral, so they're not important for what we're talking about here. Anyway, right now, sodium has, if we counted them, 11 protons here in the nucleus, and it has 11 electrons flying around outside. So the number of protons equals the number of electrons, which means that my total net charge is 0. They cancel each other out. And so something that has no net charge, like the sodium atom, we call it neutral. Okay? But here's what can happen to sodium. You see this electron right here? It can lose this electron. It can lose it, and it flies off and usually goes into another atom. So let's look at what happens when this electron here gets lost. And now we're going to end up with a sodium atom that has 11 protons, just like it did before. But now because it's lost this electron, it used to be here, that was here, now it's not here anymore. Now it only has 10 electrons. So now the positive and negative charges don't balance out anymore, and I'm left with more positive charge than negative charge. So this thing now is going to have a charge of +1, one more positive charge and negative charge. And so I can write this, if I want to talk about the atom, I can write it as Na plus to show that it has a positive charge. Whereas this, when I'm talking about a neutral atom, I'll probably just write Na. So Na plus here is an example of an ion. It's an atom that has a charge, and it's a specific type of atom. We have a name for this. We call it a cation, which is what we call an atom. An ion. We call any ion that has a positive charge. Okay? Let me show you another example. Okay, so here's an atom of oxygen. The atom that I've drawn here has 8 protons here in the nucleus and it has 8 electrons outside. So we have the same number of protons and electrons, which means that the total charges balance out, plus and minus balance out. So I have a net charge of 0, and I can say that my oxygen atom is neutral. It has no net charge. But oxygen can gain or lose electrons, and actually it really likes to gain 2 electrons. And here's a picture of the oxygen atom after it's gained 2 electrons. And now it still has 8 protons in the nucleus. And if I count up these electrons, now it has 10 electrons instead of 8, which it had before. So now the protons and electrons don't balance out anymore, and I have more negative charge than I have positive charge. I've got 2 more electrons and protons, so that means that my total net charge is going to be 2 minus. I can write the symbol for this ion as O2 minus to show that it has 2 minus charge, whereas this neutral guy over here, I can just write O. This is an ion because it has a charge, and there's a specific name for it. We can call this an anion, which is the word that we use to describe a negatively charged ion that has more electrons and protons. Okay, here's just a little bit of vocabulary for review. So an ion is an atom or a group of atoms that have a charge. Okay, now it's possible for an atom to be neutral, which means it has no charge, it means it's not an ion. But if something is an ion, it can be either a cation, which is what we call a positive ion, or it can be an anion, which is a negative ion. Here's the way that I use to remember this, okay? Anion, I think of this as standing for a negative ion, okay? And then cation, you can remember this, it's really cheesy. You can remember this because cats have pos, and a cation is positive. All right, you'll never forget, I swear, you'll never forget. Okay, there's one more thing I want to mention. I said an ion is an atom or a group of atoms with
Cats have paws. And what?
charge. I haven't said anything yet about the group of atoms. So more than one atom can come together, they can stick together and form a group or a clump, and then that whole clump of atoms has a charge. When this happens, we call it a polyatomic ion. A group of atoms have a charge. Poly means many, and atomic, you have many atoms together that form an ion. I'll talk about polyatomic ions in future videos, so you want to check those out if you need to learn more about polyatomics. Anyway, just to review what we learned. We learned that an ion is an atom or a group of atoms that have a charge, and something gets a charge when the number of protons and electrons don't balance out. You have more protons than electrons, you'll have an ion with a positive charge, you call it a cation. You have more electrons than protons, you have an ion with a negative charge, and you call that an anion.
Cation is the positive. That's an ion with a positive charge. Anion is one with a negative. Losing electrons make the charge more positive. Gaining electrons make the charge more negative. Line cation is positive. Anion is negative. So stupid. Ionic and covalent bonds. Is this even in grade 12? Like, electron configurations. This is 1 to 4. The nuclear model of the... This isn't even in grade 12. Hold on. Electron configurations. Pauli's exclusion principle. Multi-electron atoms. Bro, what am I lucky guy right now, bro?
This video is an introduction to ionic bonds and ionic bonding. Don't know anything about these things, or you feel a little bit rusty? It's no big deal, because we're going to start from scratch. So, ionic bonds are one type of chemical bond. Chemical bonds are like glue that holds atoms together. Okay, like here, two atoms.
Covalent bonds are... Yo, how did I already forget covalent bonds? Are bonds formed... Wait, no, that's not what I was looking at. I was looking at covalent... That was.
Atoms that are bonded together, connected, they're glued. Now, ionic bonds are the type of chemical bond that hold together metal atoms with non-metal atoms. Okay, so if you look at a periodic table, there's this big, thick staircase over on this side. And the staircase separates the metals, which are all the elements on this side, from the non-metals, which are most of the elements on this side. So whenever we have a chemical that has a metal connected to a non-metal, that's held together by ionic bonds. So some examples are silver chloride, magnesium iodide, or aluminum oxide. Each one of these chemicals have a metal, this one from this side of the periodic table, with a non-metal, this one from this side. So ionic bonds are all these because there are metals and non-metals connected together. Okay, so now we're going to talk a little bit more about the how and why that's going on with bonding here, right? It's like how do these atoms actually connect together? What's holding them? That's what we're going to talk about next. Okay, so learn more about ionic bonds. We're going to focus on a chemical called sodium chloride. Sodium chloride is a fancy scientific name for table salt. It's the stuff you put on your food. So sodium chloride is made of two types of atoms. We got sodium. Here's its symbol from the periodic table, and here is a sodium atom right here. And sodium chloride is also made of chlorine or chloride. I'll tell you what the difference between those is in a minute, but you don't have to worry about it right now. And here's a chlorine atom. Now, sodium chloride happens when these two atoms come together when they're glued together by ionic bonds. But the atoms that I have right here, they're not glued together. They're just kicking over together. They have nothing to do with each other. So I want to talk about what happens to get these separate atoms connected and glued together. Like these, how we go from this to this. I'm going to tell you the end of the story now so you can follow through as we go. The reason why these two atoms are connected is because they end up getting electrical charge. Okay, this atom's going to end up getting a negative charge, and this atom's going to end up getting a positive charge. What the opposite?
Dude.
Oppositely charged things like to do, they like to attract. And so because these things get different electrical charges, they are going to be held together by those different charges attracted. Okay, so let's look at the steps we have to take to go from this to this. The first step is...
OBS is using 80% of my